Previously, we have discussed the effect of additive white Gaussian noise, and now we study another channel impairment, which is intersymbol interference. So, first of all, we discuss what is intersymbol interference, and then we study the effects of, or we study the methods to remove intersymbol interference. So, for this, we consider the baseband communication system. In baseband communication system, after analog to digital converter, we have the line coder, which performs the bit to symbol mapping function. And this uh, function is an g of t. So n is the bit and g of t is the pulse shape assigned to this particular bit. So the problem with line code is that all the line codes are time limited. For example, if we consider a square wave or a rectangular wave as a representation of the line code, in frequency domain, it is a single pulse of infinite duration. So it means if we have a time limited signal, so its absolute bandwidth is infinite. And also in frequency domain, the energy of one symbol leaks into the energy of the other symbols. So it is very difficult situation to solve that the symbol smears into the adjacent symbols and causes intersymbol interference. So the other problem is that the channel is band limited. So this infinite bandwidth signal cannot be transmit over the channel. So the high frequency components will be cut off. So we don't have the sharp transitions of the pulses. So as a result, there will be a spreading of the pulses. So channel causes attenuation as well as spreading. So this spreading will result in the interference in the adjacent symbol and cause inter-symbol interference. So actually we cannot overcome inter-symbol interference, but at the receiver, we have to sample the received symbols and then we make our decision. So before sampling or at the sampling instance, we want that the interference from the adjacent symbol will be 0. So how we can done this, we will study later on. So first is we can have dispersion from the channel, and one is due to the band limited nature of the channel, and the second is if the channel is wireless, it has several multipaths, and due to the delay spread of each symbol, it smears into the other symbols. The delay spread of one symbol exceeds the symbol duration and it smears into the other symbols and causes intersymbol interference. So the other reason is that the improper filtering at transmitter and receiver is also one of the reasons that make detection of the symbol difficult. So there is a very simple NRZ line code. So we represent 1 with the positive pulse and 0 with the negative pulse. So in fact, when it passes through the channel, the output uh, will be spreaded, and the output of the bit is just like representing the channel filtering effect, which cause spreading of the symbol. So if we are considering binary communication, so these bits are in fact 2 symbols in our symbol set, and this is in fact is the um, slow transition, just like the channel acts as a filter. So as a result, if the input is um, a square wave, then the output of the channel, which is band limited or having less spread, so it has in fact is spreading in time, and energy of one symbol mixed up with the energy of another symbol. So if we sample it at these points, at these circular points, so what will happen? We have errors. So if we don't sample it at appropriate times means that the interference from the other symbol would be 0. This point and this point, so there are less chances of errors, or there are no chance of error. So for this, we use some sort of filters, which are actually the pulse shaping filters. But before discussing the pulse shaping filters, first we need to study that what are the appropriate shapes of the pulses which have 0 interference at sampling instants of time. So, so this is the summary what we have discussed so far. That ISI only occurs due to the non-band limited in time duration codes used over the band limited channel. The line codes are of infinite bandwidth, and channel has infinite bandwidth. So this is the dilemma. Here ISA can occur only at the sampling instance. So we need to overcome the intersymbol interference at the sampling instance, because before making a decision, we need to sample the received symbol, and then we will, on the basis of this sample, we will decide whether it is uh, symbol 1 or symbol 2 in a binary communication system. Overlapping pulses will not cause intersymbol interference if they have 0 amplitude at the time the signal is sampled. So if the adjacent symbol have 0 amplitude at the sampling instant, then it means there is no intersymbol interference. So the overall communication model is designed in such a way that we have the transmitter frequency response, channel frequency response, and the receiver frequency response. And we have to design the equivalent response of the system. What would be the equivalent response of the system? So for this, we are considering the impulse response of transmitter, channel, and receiver. And you can see that at the receiver output, we have this uh, signal, and the equivalent impulse response is the convolution of the impulse response of the transmitter, channel, and receiver. And in fact, the noise is convolved over the channel and receiver as well, receiver response as well. So this is the equivalent noise. So we'll see. So h of t is in fact is the equivalent impulse response of the receiving filter. Now, what we are doing that the receiver output is sampled at k instants of time. So k is in fact is the sequence of sample generated at the receiver to make decisions. So input data stream and bit superposition. So we have the equivalent model like this. So here, in fact, we need to carefully understand this part. So this part can be considered that when the input and output is perfectly, the receiver is perfectly synchronized, and the value of n is equal to k. The value of n is equal to k. So we have the desired signal h naught, desired gain parameter h naught for a of k, right? So, and for all the values when n not equal to k, we have the undesired, we have the undesired values, or we have the intersymbol interference. We are not considering the noise term here because noise is added equivalently. We consider it as a white noise, so we are not worried about it. So we are worried about this factor, which is in fact is intersymbol interference. So we want to reduce it to 0. So if this component is 0, so there is no interference in this desired component. So we model the signal in such a way that this component would be equal to 0, and we minimize the intersymbol interference. So which type of pulses satisfy this criteria? So it is in fact uh, so you can see here that we have this equivalent response is equal to 0 for n not equal to k and h not equal to 0. So which type of pulses satisfy this criteria? So uh, sync type pulses can satisfy this criteria. So sync pulse is in fact is the ideal Nyquist pulse, and the duration of this sync pulse is uh, 1 by 2b. So the duration of this sync pulse is 1 by 2b. So uh, we will see the diagram here. So there is a simple understanding of this is that what the Nyquist criteria is that uh, we transmit these sync pulses instead of rectangular pulses. So what we have to do, we have to design a filter whose frequency response is a rectangular pulse. So if we have a rectangular or we have a low pass filter at the transmitter, so we are able to transmit the pure sync pulses. So this is in fact is the pre-filter used as at the transmitter um, to generate the sync pulses. So the situation is like this. There is the amplitude 1 and the duration of this pulse is t, and the bandwidth of this is the bandwidth of this is uh, b is equal to 1 by t, 1 by t. Maybe I'm not good in writing here with the paint. So it is the value of this bandwidth is 1 by t. So so the what we have here is, so if you consider this pulse here, if you consider this pulse, so you can see that at the sampling instance, they have the subsequent pulse have non-zero value. So this is in fact is the sampling instance of the subsequent pulse. So if the impulse response of the pulse at time 0 is h of t, then the impulse response of the pulse at t time would be h of t minus t. So we are interested in sync pulses. Actually, neither we can use a rectangular filter at the transmitter because all realizable filters have not sharp transitions. So this type of filter to implement is very difficult. And the other problem, if somehow we are able to do it, even then these sync pulses are very sensitive to timing errors. So a little error in time will create problem for the system. So what we have to adjust this situation. To overcome this situation, so this is in fact is the subsequent pulses. So there is the input uh, of the low pass filter, and the output would be sync pulses, and you can see the subsequent pulses at time t0, t1, t2, t3, t4, t5, and T6, or these are the sampling instants where we sample these pulses. So these are very sensitive to timing errors. So if we see what uh, type of filters we in practice we can use. So these filters are not really rectangular and have some specific transition, and these transition from P to the actual bandwidth 1 by T is considered as a roll-off factor of 1. And similarly, we have roll-off factor from 0, which is purely a rectangular pulse, to 1, which have the excess bandwidth W. So it means that we are using twice as much bandwidth than the actual bandwidth of the rectangular filter if we are using the roll-off factor of 1. So, and if the excess bandwidth is 50%, so it means that we are using the roll-off factor of 0.5. So how roll-off factor will determine by the fact that how much excess bandwidth we used, which is which can be 50% or 100% of the actual bandwidth utilized by the rectangular filter. Now, actually, what's Nyquist criteria? What's Nyquist criteria? That if we are transmitting sync pulses, so how much bandwidth would be required? So, in fact, how many symbols we can transmit per hertz? So we can transmit RS is equal to 2W, twice of bandwidth. This is the Nyquist criteria, that our symbol rate is twice as much as the bandwidth. This is the Nyquist criteria, that these ideal pulses can be transmitted twice as much as the bandwidth. So 2 symbols per second per hertz can be transmitted without intersymbol interference. That's the Nyquist second criteria. So Nyquist criteria can be achieved with the help of sync pulses, but in practice, you know that we cannot generate ideal sync pulses because we are unable to create an ideal rectangular filter. So we have to choose some rule of factor, and we have to sacrifice some bandwidth for this purpose. So this task can be achieved by this raised cosine filter, that this component is this is in fact is this component is multiplied with the sync pulse to make it a raised cosine pulse. This raised cosine pulse have some role of factor, and that role of factor is depending on the value of alpha. Alpha is equal to R. Alpha is equal to R. So alpha is the role of factor. So by adjusting the value of alpha, you can transmit a sync like pulses, which are called raised cosine pulses. And the response of this is shown previously by this diagram. The equivalent response is shown here. The equivalent response of this raised cosine pulses is shown by this diagram, that we have the roll-off factor is 1.5 or 0. So bandwidth occupied by beyond 1 by 2t is called the excess bandwidth, and the excess bandwidth is usually expressed in percentage of the Nyquist frequency. If alpha is 0.5, then we have 50% excess bandwidth. Alpha is 1 means we have 100% excess bandwidth. This cosine filter is used to realize Nyquist physics, since the transition band can be changed using the roll-off factor, because we can adjust the roll-off factor. So the value of alpha is equal to 0 is the ideal rectangular pulse, and the bandwidth occupied by a raised cosine filter signal is increased from its minimum value. P min is equal to 1 by 2 TS. So this is the minimum bandwidth requirement of the raised cosine filter, and this is the roll-off factor. But we need a relationship between bandwidth and the symbol rate. That is more important for us. So there are few characteristics of the filter, which is in fact relating to the tabs, to how many tabs we can add and have the sharp transition, and we can have the value of alpha change according to that. Or we have, in fact, we can control the signal overshoot, uh, resulting in lower peak to mean excursion of the transmitted signal. And also we control the less sensitivity to symbol timing accuracy or wider eye opening. So these last 2 points we will discuss later on. So this is the Nyquist pulse shape, which can be written in this form. So here the bandwidth is equal to RS by 2. Because I already said that the maximum symbol rate is equal to twice of the bandwidth. It means that 2 symbols per second per hertz we can transmit, or that point or in the rectangular filter we have seen is at 1 by 2t. So this is these are the equations. If you want to plot, you can plot in MATLAB, and you can see that the response of this filter is just like I have shown you the diagrams previously. So the roll-off factor, I have already told, this is the excess bandwidth W, and this is the bandwidth of the rectangular filter W naught divided by W naught will give you the roll-off factor. If you want to calculate in percentage, so you multiply it by 100. What about the case, the bandwidth acquired by the system? if we have the Roloff factor of 1. So it means that W is equal to RS. So this relationship you can use in this formula. So because the time is short and I just giving you the answer for this is that first you need to calculate the symbol rate from this R, and you divide this R by 2, because in 4PAM we have a group of 2 bits. So you divide R by K, you will get RS, and you will put value of RS and R here, and you will get the value of W is equal to 1200 Hertz. You can see the notes I will upload on the LMS for further study or to see the solution of this example. So pulse shaping filters are implemented with FIR type filters or analog filters such as Butterworth filters may approximate the tight shape of this spectrum. Like the sync pulses, raised cosine pulses have uh, extend infinite in time. So we have to make some approximation that we need to truncate it from 3 dB to 3 dB. So the first null is at T, second null is 2T, and third null is at 3T. So there is no need to going further beyond 3T because there is very little energy outside the third lobe. So the value of alpha is 0.35 in USDC standards, and IS 95 use pulse shape slightly different than RC shapes, and European GSM using Gaussian shape pulses. So this is what are some practical aspects of pulse shaping. So actually, what we have not discussed so far is the mesh filter, and in next lecture I will also cover the mesh filter as well. So the equivalent response of transmitter and receiver would be the root raised cosine filter response. Root raised cosine filter response that there is a P filter root raised cosine at the transmitter, and there is a root raised cosine RRC filter at the receiver, and the pair of this will make a RC filter response. So you can look the diagram here that RRC pulse shape is have non-zero values at sampling is having non-zero value at sampling instance at these points. But here we have non-zero values in RRC filter. So, but we use it in a pair at transmitter and receiver. The overall response will be same like this RC. Now we use the I pattern to judge how much intersymbol interference induced by the channel. So if we transmit 1 and 0, so it is just like a box. It is just like a box you are seeing here. So, but in fact, there is no pulse like this. The actual pulse is like this, and you can see that it looks like an eye. So the maximum eye opening means that the minimum intersymbol interference, and minimum eye opening means that there is maximum intersymbol interference. So you can see an eye pattern here that there are 8 symbols transmitted by a 3-bit pattern, and we just mapped it as a map these symbols, and we have seen that the eye pattern is in this form. So we just map the first one, map the second one, third one, fourth one, fifth, and sixth, and all the subsequent over this map. And we will see that how much opening of the eye pattern. So there are multiple eye patterns in this diagram. Sometimes we have the mask region. In the mask region, there is no transmission and no waveform intrude into this mask region. So this is an eye pattern of PAM5, and you can see that 5-level PAM has a pattern like this. So what about if we have changed the value of roll-off factor, and we see that at the minimum value of roll-off factor 0.1, so we have the maximum intersymbol interference. So the overshoot of the pulse, you are seeing the overshoot here. So the overshoot of the pulse caused by filtering is greater for small alpha. So if we are choosing the small value of alpha, we have to bear this overshoot values, right? So you are not seeing any overshoot here for higher values of alpha. And in ideal case, there is no overshoot. So this overshoot encounters when we have the smaller value of alpha. So as a result, the peak signal handling requirement of the modulator and demodular circuit is increased. So um, of course, the receiver has to handle this overshoot value. So this is the eye diagram generated in MATLAB, and this is the eye diagram with noise variance 0.1, and this is with the noise variance of 0.5. So in the next lecture, we will study equalization, which is the another method to overcome intersymbol interference. And thank you very much for listening.